In this video, we're going to explore the idea of the kernel again and the idea of it collapsing dimensions by relating it back to some terminology we've seen before, specifically the terminology around injective functions. Remember, there were properties that some functions had, some didn't, of being injective and surjective. Injective is the function type that is one-to-one. Now, more formally though, which of these two definitions matches that characteristic? If a function is injective, which of these two things can you say about f? Take a moment to read those over and then make your choice. All right, before we ruin the surprise, let's remember what injective looks like. Injective is one-to-one, so if we have an output value here, let's say w on the output, there's only one v that maps to that w through that function. If we pick a different v over here, let's call it v2, it cannot map to w. It has to map to its own output, w2. And so that's this characteristic over here, where if I have two functions x and y, the output can't be the same. The output must be different if the inputs are different. And so injective is about this characteristic here. If you'd like to look at the B property, that is about surjectivity. Sometimes we talk about onto for this, or covering the output space. And it's a lovely property. It's just not related to what we need right now. If you want a quick reminder about what those injective and surjective properties look like diagrammatically, a function is surjective if you pick any output, there's only one input that traces back to it. So we see a violation. The not injective here is because A and B both map to 1. Same thing here. If I have A and B mapping to 3, two values going to the same output value, that's what makes a function not injective. Surjective is about the coverage. Every output has a matching, at least one matching input value that leads to it. But again, we're going to focus on the injectivity for this next set of slides. So here's our claim. If we have an input space V, output space W, there's a relationship between what the kernel is, and this should be a curly bracket around here because the kernel is a set. But if the kernel of L is just a single point, then we claim that it's not just about the zero vector mapping to the zero vector. It means that any point in this mapping is going to be one-to-one. And notice that this is an if and only if, and so sometimes you write that as IFF. That means we have to prove two things. That if the kernel of L is just the zero vector, then L is injective. And that if the L is injective, then the kernel of L, the things that map to the zero vector, can only be the input value 0 as well. So we are going to prove both of these, and we're going to start with the claim that if the kernel of L is just the zero vector, then L must be injective. So if we're assuming the kernel of L is just the zero vector, what does that mean? Well, it means we know that only 0 from the vector V, space V, is equal to 0 in the W space. And as a corollary to that, no other V in V satisfies the transform of V equals 0 in the output. So the only thing that maps to 0 in the output is the 0 in the input. No other random vector can do that because the kernel of L is all the values that map to 0 in the output. All right, so that's what we know. To get to injectivity, because that's what we're trying to show, to get to injectivity, let's consider two vectors, v1 and v2, in our input space. All right, and we're going to consider them such that the L of v1 equals L of v2. So that feels immediately like, well, okay, I've got v1, I've got v2, and I'm claiming they both map to the same thing, some w over here. That's only possible in an injective function if the distinction between these two vectors is actually not real, and v1 and v2 are actually the same vector in disguise, just different labels for the same thing. And then our transform reaches w in the end. So to get injectivity, consider two vectors in V such that they map to the same point. Our goal is to show that v1 must equal v2. So again, they aren't two different vectors, but if their outputs are the same, then they are actually the same as well. And all we know is the kernel property here. All right, so next up, what are we going to do here? We're going to consider that relationship. We're going to consider that L of v1 equals L of v2. Okay. How are we going to tie that back to zero vectors? Because that's what the kernel is all about, and specifically zeros in the W space. Well, what we can do here is subtract L of v2 arbitrarily from both sides. Okay, so what does that give us? Well, instead of L of v1 on the left-hand side, we're going to have L of v1 minus L of v2. And on the right-hand side, we're going to have L of v2 also minus L of v2. Now, what does that get us? Well, this lovely collection here is much better known as the zero vector in the W space. And over here we have L of v1 minus L of v2. Now, we know things about kernels. We know things about kernels. What are we trying to say? Only the zero vector maps to W. Well, here I have a sum. Could I put this into a single transform? I'd really like to put them together, because then I could talk about the transform of a single value. Well, this turns out to be equal to L of v1 minus v2. Why is that the case? Well, because L is linear. And linear functions, if I have sums or subtractions outside the transform, I can do them inside the transform first if I like. And what this is telling us is that L of v1 minus v2 maps to the zero vector. So v1 minus v2 is what? Well, it mapped to the zero vector, so it's in the kernel of L. But wait, what's our kernel? Our kernel is only the zero vector. The only thing in the kernel is a single zero vector. Is the only vector in kernel of L. So v1 minus v2 has to equal the zero vector in V. Well, what's another way to say that? v1 equals v2. And that gets our conclusion. We started with the assumption that L of v1 was equal to v2, so they both map to the same point. And because of the kernel restriction, we end up with the conclusion v1 equals v2. And so that means the function L is injective if we know just one thing, which is that the kernel of L is just the zero vector. And again, my intuition for this is that if the kernel of L is just the zero vector always maps to zero. So nothing's getting collapsed. We don't lose anything. And injectivity is about one-to-oneness as well. We don't lose any points in the transformation. Next up is to prove the opposite direction. If L is injective, then the kernel can only be the zero vector. Well, if L is injective, then only one vector, V, in the input set satisfies technically L of V equals some W, but I'm going to pick a specific W, not too surprisingly, 0. There's only one vector V that maps to the zero vector in the output. And because L is linear, one of the features of linear functions that we know whenever we transform the input vector 0, we get the output vector 0, and that means these two things here, this V and this 0, have to be the same thing, and that implies only the zero vector in V maps to the zero vector in W. So not just this value, but only that value, and that's the only value in the kernel then. So the kernel of L is equal to the zero vector in V if L is injective and linear. And there we go. We've proven both directions. If L is injective, we know the kernel is just the zero vector, and I need curly brackets around that. And likewise, we showed that if L is injective if the kernel is just the zero vector. So those two things become mutually compatible.